Okay.
All right. Well, this is a small and intimate audience, so that's great. Today we have Nirajan Dhakal, who's a assistant professor at Spelman. Before arriving at Spelman in 2015,
Yes.
he was a postdoc at UMass Amherst, and before that, here at UMaine, and his doctoral degrees from Auburn, and so you're right.
Thank you, Dr. Zain. And it feels nice to be back here at Michelle Center. I was a part of this. So today I'm going to talk about some of the work that I started, or I'm still working on it when I was at UMass Amherst. So this is the title of my topic. And if you have any question when I'm presenting, please feel free to ask me any question, okay? So I would like to start with this picture from NOAA. So this is an analysis done by NOAA showing the number of billion-dollar weather and climate disaster. And obviously there are different types of climate disaster, and one of them is flooding. Okay? So this one is the picture which shows the number of flooding across the continental USA. And since my focus is on northeastern United States, so we can see like there are a few numbers, but obviously the other climate disaster is tropical cyclone. Okay. So this is kind of one impact of the floods or high flows. If you noticed my title, my title is about high flow and low flow, and so why one of the work that I focused on is about the timing of these high flows and timing of the low flows, and this is one of the reasons why we focused on the timing of the high flows and low flows. So this is what we call is the decision calendar, the routine of the work that is done for culvert. So culvert basically are the stormwater infrastructure. And this is from the state of Vermont, and they have a specific task which they do during specific seasons because they expect certain season to be very active in terms of flooding. Especially they expect a lot of flooding events during fall events, so they do a lot of activities during summer. So removing of the blockades, repair and all the things. And they do not do a lot of activities during spring because, especially in this region, most of the time it will be kind of a lot of snow. So this is one of the things that motivated us to look at the timing of these flows. And then I was reading this paper last night, which was kind of focused on low flows. So one is about high flow, which is flooding, another is about low flows. And this is a study done by USGS. They have looked at the impact of low flow and extreme temperature changes on endangered Atlantic salmon. So basically, they're looking at how the low flows are going to impact ecosystem in the streams and rivers. So obviously, if there is a change in magnitude or seasonality of these low flows, they will have impact on the ecosystem in the rivers and streams. So I would like to first start with the statistical approach that I have used to look at the timing of these high flows and low flows. This is what I have used, which is the circular statistical approach, and we most of us hear about linear statistical approach, but circular statistical approach have not been extensively used for the climate analysis research. So circular statistical approach is basically representing the climate data as circular random variables. So if we think of a timing of these high flows or low flows in a circle in a 365 days, then we can represent a day as a circular random variable. So I don't want to spend a lot of time talking about this, but this is how this timing is converted into circular random data, basically. So if you look at this equation where we have theta I basically is an angle between 0 to 2 pi, because it's in circle the angle goes from 0 to 2 pi. Then the mean direction, in our case it will be mean timing of these high flows and low flows will be represented by theta bar, basically is given by the equation. And then the variability, I have not put equation here for the variability, but variability the spread of the data can also be estimated from this. Okay. So this is the equation basically. Variability is given by that equation, which basically shows the spread of the data. So I would like to start with what I did when I was here. Basically, I've initially looked at the timing of the precipitation, because precipitation and these flows are linked together. And we started with this initial analysis of looking at the number of precipitation events for different months. So what we can say is this is kind of a linear way of looking at this. This histogram plot shows the number of precipitation events for different months. And if you look at these figures, you can observe that these events are not distributed uniformly. They do not occur only in a specific month. Rather, they are distributed kind of in different modes. So you can see here, especially let's look at Portland. One majority of some of the events occur during spring, and the next majority occur during fall. So this is what we call the bimodal distribution of the precipitation events. And the picture on the right hand side actually shows how circular distribution can be used to visually model these events. And you can see that there are three different cases. The first one is if the data is uniformly distributed. If we have precipitation event occurring uniformly in every month, then this will be kind of distribution. However, if the data is distributed or localized in only a couple of months, then our distribution will be like a unimodal. And if the data is kind of distributed or spread around with a couple of modes, then our distribution will be like this. And as I mentioned earlier, at least for Maine, what we observed is the precipitation have distribution similar to C. Okay, so that is the reason why we had to use the circular statistical approach in order to capture these multiple modes and these extreme precipitation events. So basically, what this shows is the difference between the circular density approach versus some of the non-parametric test. And the reason I'm showing all this is just to show that this approach is more robust as compared to the linear approach or some non-parametric test, because this test, which is called the Rao spacing test, is considered to be the most robust non-parametric test. But even this test cannot capture the multimodality of case C. If you look at the test result, this is a trimodal case, and a Rao spacing test does not confirm that there is a trimodal case here, because it does the hypothesis is rejected. Okay, so that's the reason we need to use the circular approach. And this is the result for the precipitation timing distribution across the state of Maine. And if we look at it a little bit closely, then what we can see is, especially for majority of the stations, there is appearance of the modes during spring season, late spring or early summer. Okay, and this is a kind of a regional assessment that we did for the Northeast. And even for the regional assessment, we can see that these modes appear during spring. So this shows that there is actually appearance of the precipitation modes during spring as well as early summer. Okay. So now I want to focus on non-stationarity of river flows. So obviously, assessment of river flows is more complicated as compared to precipitation assessment, because when we talk about river flows, then it is influenced by multiple factors. So both anthropogenic and climate influence may have impacted the river flows, including the land use change, which is a big thing, especially in the rapidly urbanizing watersheds. And land use change through changes in subsurface flow and groundwater recharge is going to impact the river flows. Either it can be high flows or low flows. And obviously changes in precipitation and evaporation have also impacts on the river flows. And when we talk about non-stationarity in river flows, the river flow can show two types of non-stationarity, which is gradually increasing or decreasing trends and abrupt changes in the mean or variability. So if we look at a number of literature, a number of work which has been focused on looking at the changing characteristics of these river flows, they have focused on both of these, looking at the abrupt change as well as gradually increasing or decreasing trends. Okay. However, we made some simplification that step changes, abrupt and visually obvious in the time series, are indicative of an anthropogenic effect, and that gradual trends reflect a climate effect, which may be due to anthropogenic climate change or long-term persistence. So our focus is to use non-parametric statistical approach to identify gradual changes in the value and timing of river flows, but we did not focus on any anthropogenic impact, which may include land use change or so on, or construction of dams along the rivers. So basically, I used the circular statistical approach to look at the seasonality of the high flows for the last 60 years in northeastern stations. So these stations are extracted from the USGS SCDN sites. So basically these sites are considered to be comparatively relatively free of anthropogenic effect, especially they are not considered to be impacted by the dams, because these rivers have very less number of dams. Okay, so the data period is from 1951 to 2010, and at least for the high flow, I use only one index, which is the 1-day annual maximum flow. But we can obviously expand this to look at the peak over threshold and so on. And so this plot shows the mean direction plot, which is indicated by the direction of the arrows, and the length of the arrow shows the strength or the spread of the data. And what we observed, if you look at the histogram which has been plotted here, majority of these high flows occur during the months of February, March, and April, and which is understandable because most of these watersheds are dominated by snowmelt. And we wanted to look at if there has been any change in timing of this and 1 day annual maximum flow. So what I did is I divided the data into two blocks. So first 30 years and the second 30 year. Okay. And I simply plotted this is vector plot. So basically vector plot shows the mean direction as well as the strength, the spread of this data. And what I noticed, although it's difficult to, I think, see on these plots, is weakening of seasonality strength for a number of sites for the recent time period. So basically this strength indicated by the row is getting smaller. Okay. And this can be seen from here also. So this blue color represents the earlier time period and the red color represents the most recent time period. And obviously, if you think of the mean direction, which is the mean timing of these flows, is around the same month, which is spring. But if you look here, these values are changing. So, and I forgot to mention, if the value of this row is 1, that means the seasonality is really strong. That means it's a unimodal. And if it's close to 0, then it's getting kind of spread out and showing maybe modes, multiple modes. So at least here I observe that some of these values are kind of decreasing. Okay, so and I did a uniformity test, and what I observed is at least for most recent time period, there are a number of stations kind of showing uniform flows, and this agrees with our previous observations that the value of this strength or the spread of the data are getting smaller. And then I use the distribution, the circular kernel distribution to look at the seasonality of these each of these stations individually. And this is one example. Although we got mixed results, but this example kind of shows one good result, at least in terms of the strength or the robustness of this approach and what we observed in the previous two slides that I presented. So basically, if we look at this distribution, at least for this station, what we see is for the recent time period, the stream flow are showing multiple modes. And obviously, there is a strong mode during the spring and early summer, which is understandable, but at least for the recent time period, we can see there is emergence of modes in summer as well as fall. Okay. And so what I did is I developed this kind of density, kernel density for each of the stations, and counted the number of stations with significant density for each of these days for earlier time period as well as the most recent time period. And this is what I obtained. So as expected, most of these stations have their modes during winter, spring season. But the interesting thing is, for the most recent time period, we see a number of emergence of modes during fall season, and some during summer season as well. And one of the reasons might be, again, we have to think about number of anthropogenic impacts and so on, but one of the climatic reasons, which I thought might be the influence of tropical cyclones. So we know that North Atlantic tropical cyclones has an impact on the precipitation as well as the river flows in this region. So I just wanted to look at this, why this is happening. Okay, and so what I did is, first thing is, I extracted the stations with unique seasonal mode. So basically, I wanted to look at what are the stations that are showing this, or what are the stations that are showing this. Okay, so I looked at the stations with unique seasonal mode for the earlier time period versus the recent time period, and interestingly, uh, along these coastal states, I observed that these states along the coast, they have unique seasonal mode during spring as well as fall. Okay? And one of the reasons for this might be what I showed for precipitation, that the timing of this precipitation have been shifting earlier. And another reason for this fall modes might be due to the tropical cyclone. And just to verify that, or just to confirm or check that, what I did is I counted a number of tropical cyclone induced high flow events along the northeast uh, from 1960 to 2011 uh, and plotted it. So basically, what I did is, if any flood event occurred within plus minus 3 days of a tropical cyclone track, because we have this track data from NOAA, and we should be able to calculate the distance between this track and the stations. So if the station river flow gauging station is within a certain buffering zone, and if the station experience a high flow during that time frame, then we can say, okay, there is a high chance that the flood is caused by the tropical cyclone. So I use that criteria to look at the number of the count of the TC-induced high flow events, and this is what I observed. So basically, this is interesting because there is some sort of variation, a decadal variation in the count of these TC-induced high flow events. But if we look at this plot, if you look at this plot after 1990, then we can see unusually high flow events is caused by tropical cyclones. So one of the work which I have been doing with Dr. Jain is about how these tropical cyclones have been impacting the precipitation extremes distribution along the northeast. And this kind of actually is a work that supports our that work also related to precipitation. Okay. And then I wanted to look at the role of large-scale climate variability. So here I explored the role of El Nino, but I did not specifically observe any kind of influence, at least when I compared negative and positive phase of El Nino. But I think if I compare this with the non-El Nino years, I might be able to see some of the impact of the large-scale climate variability. And I was expecting, at least for the El Nino positive phase, to be a little bit more active during winter because it's a warm phase. But interestingly, this uniformity test shows some interesting results, at least for the El Nino versus La Nina year. So number of these stations are now showing uniform mode for both El Nino and La Nina years. So I have not been able to explore why this is happening, but this is what I observed. So that was about timing of the high flows. Then there are a number of studies which have already looked at the trends in the magnitude of these high flows. And what I observed from my experiment or analysis is similar to what they have observed. There is not any kind of significant increasing trend in these high flow events. So this is what is, I think it's not very clear, the picture, but I use Min-Kendall non-parametric test to look at the trends in these high flow high flow events, and only few events for both the time periods shows some significant trend. And then I wanted to look at how if there is any trend, or if there is any change in the 100-year flood event. So basically, here what I did is I estimated 100-year flood event based on the previous 30-year data and most recent 30-year data, and plotted the ratio of this new estimate versus the old estimate. So basically, if the ratio is bigger than 1, then then that is increase in the 100-year flood event. And I did a Kriging interpolation to do the density plot of this 100-year flood ratio, we can say that. And the result is also mixed. It's kind of sporadic, as expected. If we compare this versus this, that's what we we can match these two results. So some regions they are showing increase in the 100-year flood events. Some regions are not showing. Some regions are showing decrease, and they are not spatially kind of coherent. So this is about high flow, and then I have started looking at the low flow indices. So for low flow, people normally look at n-day minimum flows. So a low flow can be 1-day minimum flow, or the most extensively used, the most popular is 7 consecutive day average minimum flow. And a 30-day average minimum flow is another index that I am planning to explore. And some of other researchers have even looked at 90-day average minimum flow. And so basically, each of these indices have their own significance and their impact. Normally, 7-day minimum flow is considered a dry weather flow. Q1 has an impact on ecological assessment, like the USGS report which I showed at the beginning. And Q30 has an impact on the reservoir operations, and so on. So similar to the high flow, I just want to look at what is seasonality of this Q1 and Q7 low flows. And interestingly, what I observed, at least for the low flows, the seasonality is really strong. So if you look at this histogram, we observe that either for Q1 or Q7, which is 1-day minimum flow and 7 consecutive day average minimum flow, they have a strong mode. They're kind of unimodal in terms of their timing during July and August for both of these flow indices. So since that seasonality is so strong, as expected, I wanted to look at the non-stationarity and see if there is any change in seasonality of Q1 and Q7. I'm here presenting the result for only Q7, and I still have to work for Q30 and Q90. But I did not find any change in the timing of these low flows, as expected from our first result. And is a similar is the result with the number of stations showing the significant modes that is obtained from the circular distribution. And this is the result as expected, that most of these flows are strongly unimodal and occurring between July to August or to September. This is one of the work which is done by my colleague at UMass Amherst, and he, as I mentioned earlier, a number of work has been done already to look at the magnitude of these low flows and high flows. And the top figure is for the trend in high flows, and I already discussed about this high flow trend. There is not any kind of significant trend in high flows, at least for the northeast. Only few stations show the trend, significant trends. But surprisingly, for the low flows, it shows a lot more significant trends. And this is a 7-day minimum low flow. And this is the work done by Sadri et al. And he also looked at the trend of Q7 and Q30 along the northeast. And the results are somewhat interesting. So especially here, there is an increasing trend for the Q7 as was observed by my colleague, and even for Q30 there is some sort of coherence between Q7 and Q30 in terms of increase in the Q7 flows, low flows. So this is a work in progress, and I want to expand it to look at Q30, Q90 timing and so on. But this is what I have up to now. And if you have any question, I'll be glad to take it. Thank you.
Comments?
Yes.
A quick question. Really cool talk. Thanks for
Thank you.
giving it. Have you compared the patterns in seasonality to the spatial pattern of changing snowpack over the years?
Not really, not really. So yeah, that's one of the work that I am planning to do. So because we have been talking about this kind of distribution, mixture distribution. So basically, we can differentiate between the flood generated by snowmelt versus regular precipitation. So that was one of the motive of the work that I have been planning to do, but I have not looked at it yet. That's a good suggestion.
Other questions?
Yes.
So also, like I saw that you explained the increase in flows during the fall season due to the frost cycle.
Yeah.
But what about, say, for instance, especially the regions that show that chains were in the southern New England regions or even the mid-Atlantic regions, right? So, like we see that even like snowfall in the fall region, in the fall or in winter regions are now becoming rainfall events. So can it be one explanation to why we see?
Yeah, I mean that snow mixed with rain. That's what we call, right? Yeah. If as I mentioned earlier, there can be a number of climatological causes that has caused that increase in the modes. And I looked at tropical cyclones only, but yeah, that might be another possible cause. Yeah, that's correct. Yeah. Thank you very much.